Whenever we look at data, we're really just trying to find a clear signal hiding in a whole lot of noise. It's a huge challenge that researchers and scientists deal with every single day. How do you make the best possible decision when the information you have is, well, uncertain?
Just think about this for a second. Let's say a new vaccine gets developed. The clinical trial data comes back. Now what? How do we decide with real confidence if this thing is a genuine breakthrough or if the results we're seeing are just a fluke, random chance? The stakes really could not be higher.
So, to get an answer, we need a statistical test. But that leads to the real question, the one we're going to dig into right now. There are tons of ways to analyze data, so how do we know we're using the best one, the most powerful test, the one that's going to give us the clearest possible answer?
Okay, so let's get into it. The very first thing you do in any statistical test is you set up two competing stories, two versions of reality. We call these hypotheses. It's kind of like you're setting the stage for a debate where there can only be one winner.
So on one side, you've got the null hypothesis. You'll see it written as H0. This is basically the skeptic's view. It's the default position that nothing interesting is happening. So for our vaccine, it said it has absolutely no effect. Then, on the other side, you have the alternative hypothesis, or HA. This is the story the researcher is usually hoping is true, that the vaccine does have a real, measurable effect. The whole job of our test is to look at the evidence and decide which of these two stories it supports.
Now here's something that is absolutely crucial to understand. No test is ever perfect. When we make a decision with data, there's always a risk that we'll get it wrong. And it turns out there are exactly two ways we can mess up. Let's break this down. Any test gives you 4 possible outcomes. 2 of them are great. We got it right. We either correctly say there's no effect when there isn't one, or we correctly spot an effect that's really there. But those other 2 boxes, well, those are the errors. And they represent this fundamental trade-off that exists in every single statistical decision.
So, a type 1 error, that's what we call a false positive. It's when we shout from the rooftops that the vaccine works, but in reality, it's useless. A type 2 error is the exact opposite, a false negative. This means the vaccine is a miracle cure, but our test completely missed it. We failed to see the effect. Obviously, both of these are bad news, but they have very different consequences.
So with this trade-off on the table, the scientific community had to make a choice. And they pretty much decided that one of these errors is generally way worse than the other, the false positive. I mean, think about it. Claiming a dud treatment actually works can be dangerous. So priority number 1 became controlling the rate of these type 1 errors.
And how do they do that? Well, they draw a line in the sand before a single piece of data is even collected. This line is called the significance level, or alpha. And you've probably seen this number a million times. Alpha equals 0.05. What this means is we're agreeing upfront to accept no more than a 5% chance of making a false positive error.
So officially, alpha is the maximum risk of a false positive that we are willing to put up with. Setting this limit beforehand is so important because it keeps us honest. It ensures our own hopes and biases don't creep in and influence the results. It's like we're locking in the rules of the game before the game even starts.
Okay, so we've put a cap on our risk of a false positive. We've locked it in at 5%. What's next? Well, now our goal is to tackle the other kind of error, the type 2 error. And reducing that error is the very same thing as maximizing our test's power. Statistical power is such a cool idea. It's just the probability that your test will actually find a real effect, assuming one is out there to be found. A high-power test is like a really sensitive smoke detector. It's just great at picking up the signal. Our mission then is to build the most powerful test imaginable while sticking to our 5% alpha rule.
So how do we get more power? Well, sure, if the vaccine had a massive effect, it'd be easier to spot. We could also just raise our alpha level, but no, we've already agreed to keep that at 5%. The most common way to boost power, and the one we can control, is to increase our sample size, right? More data usually gives you a clearer signal. But what if our data is already collected? Can we design the test itself to squeeze out the most power?
And that brings us to the main event. Back in the 1930s, 2 statisticians, Neyman and Neyman-Pearson, came up with this absolutely revolutionary answer. It's a mathematical proof called the Neyman-Pearson lemma, and it basically gives us the exact recipe for the most powerful test possible.
The core idea is this. The lemma gives us a method to find an optimal test, let's call it C-star. And what it proves, mathematically, is that this C-star test will always have more power than any other possible test, which we can call C, that has the same alpha level. It is quite literally the undisputed champion.
So what's the secret? What's this amazing recipe that Neyman and Pearson discovered? Well, it all boils down to one simple, elegant idea. To get the most powerful test, your entire decision has to be based on something called the likelihood ratio.
Now, likelihood ratio might sound super technical, but the concept is actually pretty intuitive. Here's how it works. Step 1. You figure out how likely it is you'd see your data if the vaccine really works. That's the alternative hypothesis. Step 2. You figure out how likely you'd see the exact same data if the vaccine does nothing. That's the null. Step 3. You make a ratio, dividing the first number by the second. And finally, if that ratio is really big, meaning your data are way more likely under the "it works" story, then you reject the null. That's it. It's a statistical tug-of-war, and the lemma proves this is the best way to pick a winner.
So you might be wondering, why are we talking about some statistical theory from almost 100 years ago? Well, because this lemma isn't just a historical curiosity. It is the theoretical backbone for how we make thousands of critical decisions in medicine, science, and engineering, even today.
All right, let's pull this all together. At its core, hypothesis testing is all about managing that trade-off between two ways of being wrong. The scientific standard is to first lock down our tolerance for a false positive, our alpha. After that, the entire game is about maximizing our power, our ability to find an effect if it's really there. And the Neyman-Pearson lemma, that's our ultimate guide. It gives us the mathematical blueprint for building the single most powerful test there is.
In the end, this lemma is so much more than just a math formula. It's a way of thinking, a logical framework for weighing evidence and making the best choice you can. And it leaves us with this really deep question that goes way beyond statistics. In a world that's filled with uncertainty, how do any of us find the best possible way to balance the risk of being wrong with the incredible reward of finding out we're right?